We are talking about analogy of normals, means how why we calculate normals and how we calculate normal in 3D graphics OpenGL. So normal always comes as a kind of matter or matrix of confusion, and why we want normal and how it is different to rest of the things, kind of in, I would say, vectors. Okay, so there are two things in OpenGL. One is surface, means one is model. Model has vertices, and other is normal. So model is nothing but it's a surface, like, but in kind of in digital world there is nothing analogous. There is nothing kind of that is continuous. So means in analog way. Uh, so there is no continuous surface. So it's a set of surfaces like triangles. So many triangles, they constitute a surface. So surface is nothing but it's a kind of a plane which has minimal three vertices. So if I have a three vertices, if I connect it, then minimum I can make a triangle and it has a surface. Okay. So surface has three vertices, and each vertices I can say that two vectors they meet at vertex. So that is the vertex. But what about normal? Normal is not a surface. Normal is the direction. What is the surface and what is the direction? If normal is the direction and surface is a kind of, it has a direction and position. So we now we have three main transformation, like translation, and we have rotation, and then we have scale. So if I talk about surface, it constitutes everything. But if I talk about a normal, it's a vector. Vector means it has a direction, okay, and it has a position. It doesn't have any position. A surface has a position. Surface can be scaled, and surface can be transformed in translation. Surface can be rotated. A normal is a direction. If it is a direction, neither it can be scaled nor it can be translated. It can only be rotated. Okay? So that is the big difference between a surface and a normal. So whatever the lighting calculation we have seen, we do in normals. I mean, we do in directions. We don't do in surfaces. So if I am doing lighting calculation to the surface, somehow we try to get the directions. That we kind of cross. Okay. Now, what is the analogy of what is the relationship, I would say, between the surface and the normal? Okay. So normal is if I believe that surface, okay, surface is nothing but it's a plane. Surface can be 3D, like I have a sphere, okay, and a sphere is 3 dimensional, it's not 2 dimensional. If I try to get a plane at any point on the surface, if I have a sphere, at any point on the sphere, I say that this is the surface at this point. But this is physically possible in OpenGL because there is no kind of analog things. So things are discrete. So everywhere there are triangles, okay, or quad or whatsoever. But it is not analogous. So in that way, if I have a surface, okay, I am talking about analytical surfaces. So two kind of surfaces are there. One is analytical surfaces, means continuous surfaces. That is based upon analytical equation. X square plus y square plus z square equal to radius square. So that is the equation of a sphere. Okay, so x square plus y square plus. So this is analogous. We call it analytical surface. So it is based upon some equation. And there is another kind of like polygon data. Okay, so we have many polygons. The way we are talking in OpenGL. So we have kind of triangles. So now if I have a kind of surface, so if I have a surface and I am trying to find normal at any point, so my surface is 3D surface and I am trying to find normal at any point, then can I find a 2D surface? So at any point, can I say that at this point, this surface makes sense? I have a 3D surface. On the surface, there is any point. At that point, I place a 2D surface. And I say, this is the surface that belongs to this point. If I know the surface, then I can get the normal vector from the surface. So a surface is nothing but, as I said, a surface is nothing but, if it is a 2D, then two vectors would make the surface. Like if I have an xy surface, xy surface means one line in x direction, one line in y direction. If I think about it, then it becomes a surface. But behind the surface, there is only two lines. So if I am able to find two lines, then I can think about a surface. Okay? Or, anyway, if you have surface, then there is a two line behind the scene. Now, if I have two lines, then there is a surface, this line, surface, and then normal. Okay, so the two lines need to be. Now, I have to find kind of cross product. So if I cross these two lines, then I know the normal. So we are talking about how to calculate normal. If I have analytical surface, a surface through formula, or I have polygon data, set of triangles, set of chords, how I can find the normal? So if I have analytical surface, then at any point I would try to find the kind of tangent. If I have a sphere, at any point I have to find the tangent in two directions, x direction, y direction. If I find the tangent in two directions, then surface is ready. If surface is ready, then two directions cross and we find the norm. So that is the way we calculate the norm. There are two ways again in the analysis. So we are talking about analytical surface. So in analytical surfaces, we find that at any point, any vertex, we try to find the surface, and from that surface we find the norm. Okay, there is explicit way that analytical surface is mentioned. Okay, that we will see, and then the implicit way like x square, y square, z square. So that if I have my explicit way is very difficult, because if I have explicit way, I'll try to find derivative so that I can get the tangent, and if I get two tangents in two directions, surface is made and then normal. Or if I am getting the implicit way, okay, then means I am not getting one surface and normal. Then I can think about gradient. So if I get the gradient, like if I have three coordinate surfaces, then all three gradient, if I get a derivative at that point or derivative equation, then also we can find the normal. That means now in the polygon data, how we find the normal? I think implicitly we have done. So if I have a polygon data, then already if polygon data is a triangle, then already I have a surface. Everywhere surface is different. Okay, so many triangles are there. One triangle, okay, in one triangle the normal would be seen all the vertices. So doing cross of any two lines and I can find the normal. Or in the particular region, okay, we can do averaging or some kind of intelligence. Depends upon the surface. If surface is like this, then this and this, we can just two normals we can average. If surface is like this, okay, then we cannot do averaging. So those conditions that will then the most awaited, okay, that is the transformation. So that later in the discussion we'll see that first we'll see that if I have a static surface, then how I can find the normal. Normal is not a surface. I cannot imagine that normal is a perpendicular surface on the surface. Normal is a pure direction. Direction has no surface. Direction can have magnitude and direction is direction. So one vector can have a magnitude and it can have a direction. So you can refer to kind of a vector tutorial on the vectors. So first we'll calculate the static normals from the surface and then we'll see the transformation. So that is further discussion on the surface and normal and then surface transformation, normal transformation. Okay, so we'll proceed. So this is Linux Mint. Okay, so discussion is on surface, normal transformation, surface transformation. Okay, how they are related to each other. So surface is area, surface is area, surface is an area. Surface needs at least three vertices. If three vertices are available, then it is a surface. Where a normal is a direction, surface is an area, normal is a direction, it has magnitude and direction, normal is a vector, surface is not a vector. Okay, surface can have direction, we can think about it, but it's not kind of, like normal, there is a difference. Like if I have three vertices, if I add edges, it becomes a triangle, and if I fill it, it becomes a surface. So surface has area. If I have only one point, this makes a normal, a vector. Means if I draw from the origin, if I draw okay, so from origin, if I draw a line, okay, so this is Mr. Origin, and if I draw a line from origin to this point, this line is the vector. So if this point is P, any P, then the vector equation will be P. Okay, this is one vector. So it has direction, we can see, and it has magnitude. Okay, so if it is okay, so if this point corresponds to P, okay, if this point corresponds to P, then this is a vector and its magnitude can be represented as P, or we can say like if it is x, y, z, then x square plus y square plus z square, okay, and a square root. So x square plus y square, and then plus z square, and then square root. So this is also called Euclidean space. And then a square root. So that is also a kind of so this is the magnitude of the vector. So that is P, or x square plus y square plus z square. So with one point also we can represent a vector, or if I have 2 points P1 and P2, then the line that is passing through P1 and P2, that is P1 minus P2. So that is the vector. Okay. Now at a single point, if I draw a parallel to this line, okay, so if this is the line, if I draw exactly parallel to this line and it passes through origin, okay, then P1 minus P2, so P1 minus P2 is the new vector. P1 minus P2 would be some xyz, and that is, so if P1 is x1, y1, z1, P2 is x2, y2, z2, this would lead to x1 minus x2, y1 minus y2, z1 minus z2. So there will be x, y, z. This is net x, y, z. And that is, if I draw from the origin a line, so this is this vector. So if I have 2 points P1 and P2 and a line passes through P1 and P2, that vector is actually this one, not this one, what we think. Okay, the direction of vector is from the origin. If I have the net xyz, then this is the vector. So we have surface and this is the vector. So vector can be represented as 1 point, 1 vertices, and a line passing from origin to that point. So that is the vector. Okay. Now we can calculate what would be its magnitude. So a vector has magnitude and direction. You can refer to a vector tutorial. Okay, what we want? Now, if I see the surface can be of 2 types, polygon data. Can we see so many polygons? These are square. Okay, so these are quad. This can be a triangular polygon also. Okay, so I can have a sphere. Okay, so this is a sphere. I can make it big. Okay, so this is a sphere, and now, okay, can we see now it's triangles? So earlier it is quad and then it is triangle. So a polygon, so a surface can be like it is a sphere and its surface can be set of polygons. That is what we are saying. Or it can be completely smooth. It is called analytic surface. Okay. So analytic surface is like which can be represented by an equation where this is set of polygon data. So these are polygon 1 polygon, 2 polygon, 3 polygon, 4th polygon, 5th polygon is set of polygon where this is analytical surface. Surface can be in both ways. Okay. So surface can be represented as polynomial equation. So I can say it as x x square plus y square plus z square minus k, or minus if it is unit, equal to 0. Okay, so this is the equation of this sphere. Any sphere s square minus. Okay, so a surface is of 2. What we are planning to do now? So if I have two surfaces, kind of surfaces, what we want? We want to calculate the normal. So that is the idea. Like at any point, what would be the direction of normal? At any point, what would be the direction of normal? Anyway, here at all points, direction of the normal are same. This is what we want to calculate. What is the normal? Okay, so what is the normal? What is the normal? So that is the question. Okay, so what is the normal? At any point, what is the normal? Now, the analytical surface, what we are saying, it is of two types. One is like we can define a surface, that is kind of where the independent variable are 2. So it is kind of based upon s and t. So s is x kind of, and t is y, and r is z, str. This is generally used in texturing. Okay, so this is a function vst, and it has a kind of 3 points, x, y, and z. Sorry, 3 equations corresponds to this function. Okay, so x, y, and z. Okay, so a function with kind of variation in st, that is x, again y, again z. If that is the situation, if that is the polynomial equation, this is called explicit surface definition. And if I have in x, y, z equal to 0, then this is implicit surface definition. Okay. Now we want to calculate the area of a surface. So if this is a sphere, okay, now if I draw a sphere like this at any point, okay, if I do the derivative, differentiation along the s direction, so it will give kind of a tangent. If I do the differentiation along y direction, it will give another tangent. Now, two tangents are available in s direction, in t direction. Okay. Now, it would look like perpendicular to each other, s and t. Okay. So, what we are trying to find is, we are trying to find one surface
that will be kind of, now we are talking about a line that is tangent. Can we think about a surface? Okay, so can we think about a surface? Okay, at any point can we think about a surface? Okay, so at any point can we think about a surface that will kind of, I'm not able to draw it nicely. So that will just sit on top of it. So this is the surface that is kind of sitting just on top of it. Okay, so this is better drawn like this. So now there is a surface that sits exactly on top of it, and at this point we can say, now I am saying this is a tangent in y direction, in t direction, this is a tangent in x direction. Now we can say this as a surface at this point that is tangent at that point on the sphere. So a sphere is 3D, then its tangent is 2D. So if tangent is surface, then there are two vectors, this vector and this vector. We can say as v1 and v2. If we calculate cross of v1 and v2, we can calculate the normal. That is the story. So if I have a analytical surface 3D at any point, that is explicit surface definition, means that is variable only in S and T. And if that is the equation, if I calculate tangent in S direction and in T direction, so it would look like this at any point. This corresponds to two vectors. If there are two vectors, then they correspond to a kind of a surface. Okay, so if they correspond to kind of a surface, I can draw a surface like this. I believe this would be better. I can draw a surface like this. So this is nothing but a surface. Surface just exactly sitting on the sphere on 3D diagram. Okay, so that is the idea. So if I get the exact surface with the two tangents, then I can calculate the normal. Then here I can calculate the normal. So calculating the normal is nothing but, if I have two vectors, if I do the cross, then I get the normal. Okay, exactly like this. So if this one vector is like this, another vector is like this, like if I have a triangle and one vector is like this, one vector is like this, the normal would be v1 cross v2. This is what we want. So in analytical surface, we calculate two tangents, and based upon the two tangent, we estimate the area, and that area okay, so that area we calculate the cross, and then that is the normal. This is the way we do. Now let's take example of a sphere. So VSTR, but actually it should be VST, but anyway, STR equal to 1. So this is the equation. So if I say R equal to 1 minus ST. Okay, so explicit way we have to specify VST. So this would be S in X direction, T in Y direction, and G any function ST in the Z direction. So that is like this. VST equal to ST. This is explicit differential. We are talking about explicit difference. So this is x, y and z, that is kind of dependent upon these variables s, t. For a sphere it leads to like this, s, t, then along the r it is 1 minus s square and t square the square root. Okay. Now the vector v1, that is s and t, these two we can calculate like dvst by ds and dvst by dt. Okay, if that is the case, then v1, the vector, now two vectors are coming, v1 and v2. So one vector would be 1. So if I differentiate with s, this would be 1, this would be 0, and this would be 1 minus s square minus t square to the power 1 by 2. So that will be 1 by 2 into 1 minus s square minus t square to the power minus 1 by 2. So there is a chain rule, and then we will differentiate again. So it will come as minus 2s. So 2 we can cancel, and then it will lead to minus s into 1 minus s square minus t square to the power minus 1 by 2. That is the way we do the chain rule in the differentiation. And just for the brevity, we have not added the calculation. So now it would be 1, 0 and minus s and cross. So this is v1 and this is v2. If this is v2, then the differentiation of s, now we are calculating v2. So dvst by dt. So this is the differentiation. So this would be 0, this would be 1, and this would be again 1 by 2, 1 minus s square minus t square to the power of minus 1 by 2. Please refer to differentiation calculus tutorial, differentiation and integration. And minus 1 minus s square minus t square to the power minus 1 by 2, because we have to minus 1, 1 by 2 minus 1 is minus 1 by 2. Then again chain rule, it will be minus 2t, so it will lead to minus t by minus s, 1 minus s square. So these are two vertex we are getting. So we are getting s and t. If we are getting two vertices that constitute to a surface, then normal will be cross of these two. Okay. Now the cross of these two, that there is a formula for that. If this is A, B and C, A1, B1 and C1, this is A2, B2 and C2. So there is a formula to calculate, and we calculated. This would lead to something like I believe so, like okay, so A2 and okay, A1 2 and B2 3 minus something like that. Okay, so that is the cross. So we calculated, and it comes to minus s by this, t by this, and 1. So this is the normal what we are talking. So we got the normal. So in s direction normal is this, in t direction normal is this, and in z direction normal means in r direction normal is 1. So we will do the normalization. So normalization is nothing but what normal we calculated by its magnitude. Okay, so magnitude is nothing but, okay, so magnitude if we want, then this square plus this square plus this square to the square root. So that will lead to s square plus t square plus 1 by 1 minus s square minus t square to the square root. Then it will finally come to like this. If this is true, then it will be s by, okay, so now we have to divide n by magnitude. So that would lead to s by this, t by this, and then 1 minus s square t square this. If I see only the direction, then it will come as st and like. So this is the, finally we are getting normal at any point s, t and the GST, GST, okay. So s, t and GST. So ST and GST is this. So this is the normal we are getting. Now we will calculate. If n is, can we see the elegance? This is, we have not mentioned. The elegance of explicit formula is, we don't have to worry about the points. Point we can just place and we get the, means it is just amazing. Okay. So I can just give 1, 0, S direction 1 and Y direction 0. It would lead to 1, 0, 0. So S direction 1, 1, Y direction 0, and then it would lead to 1 minus 1, 0. So it will be 1, 0, 0. So here in S, this point we are talking 1, 0. So it will be outwards, that is the normal. This is what we want. In Y direction, it will be like this. And where Z is 1 and XY are 0, it will be like this. Okay, now at places where both are 0.5, 0.5, okay, so it would be somewhere here, okay. Okay, so what we are saying is something like this, okay, somewhere in X direction here, and then inside Y, okay, some direction here, and then it will be, I believe it is understandable. So it would be inside the sphere, it will be at this point, and then in Z direction we have to think, okay, but okay, so now we don't have to worry about Z. This is the class of this explicit definition of the analytical surface. I just say X and Y 0.5, 0.5, then it is 0.5, 0.5 as per the equation ST, and 1 minus S square and T square. So 0.25, 0.25, 1 minus 0.5, 0.5 to the square root. So that would come as 707. Okay. What about 0.5 and 0? So in X direction 0.5, Y direction 0, we don't worry about where it hits on the top. But it will be greater, okay, than this Z. So it will be 0.50, 0.866. So T is 0, S is 0.5, this will 0.25, and then 1 minus 0.25, 0.75. Okay. Import math dot square root, okay, 1 minus 0.5 into 0.5, 0.866, So if we are on x-axis, then z will be more. If we go towards y-axis, okay, then z will be lower. So that is the idea. At the center, both will be kind of okay. So center, at the center there is nothing. Means I believe there won't be any surface touching. So other point that we calculate. Okay, so we finished the analytical surface, explicit surface definition. Now what we need to do is we have to find the surface equation that is based upon S and T, not in R. S, T and GST. Once we get, then we have to do the differentiation and we calculate the two vector, and after calculating two vector we do the cross. Once we find the new normal, we do the normalization and we get the actual normal direction. We are talking about normal direction, this one, not this one. If we do P1 minus P2, it leads to the actual vector direction. Okay, normal is a vector. Okay, vector has its own rule and regulation. It's not that easy. Okay, it can make someone's life hell, this vector direction. Okay, now we'll see, so we finish this, now we'll see the implicit definition, implicit surface definition. Now if this is the surface, I mean a sphere, then implicit surface definition leads to fxyz equal to 0. Okay, and then we have to calculate the formula like this: x square plus y square plus z square minus 1 equal to 0. Now we find the gradient in x, in y and z. If I calculate like this, 3 gradients, net gradient, then we can get the normal. So easy. So that will be 2x, 2y and 2z in direction of x, y, z. Relax. So this is far better than explicit, but there is a caveat. Caveat is estimating x, y, z is very difficult. Here it is in equation of 2 only, s and t. Here it is x, y, z, and it is very difficult. So this is better. Means we get in the kind of in variation of only s and t. Here I have to calculate x, y. So getting the actual point on all point on surfaces to calculate the normal is very difficult. Anyway, but we'll do. Can we see it is similar? S, t, and if I say 1 minus s square by t square, it is x, y, z. It is similar. Anyways, now if we have find x, y, z, then x 0, 1, 0, 0, it will be 1, 0, 0, 0, 1, 0, it will be 0, 1, 0, and 0, 1, it will be 0, 0, 1, exactly like this what we calculated. Here we calculated with this formula, 1 minus s square t square. Here it is direct, but we have to find, now this is difficult, the way we are saying. Now if x is 0.5, y is 0.5, what will be z? So that we have to calculate based upon this formula. And then at that point, the normal would be 5.5 and this lead to 0.707. So it is exactly like this. So this is the way we calculate the polynomial analytical surface normal. Okay, there are 2 ways. One way we calculate the gradient, okay, and for direction of x, y and z, and calculating the points are difficult. But here in explicit, we just say s and t and gst, and then we calculate v1 and v2. If we get v1 and v2, we calculate the cross to get the normal as per the vector analogy. And once we get cross, we do the normalization and we try to get the actual normal direction, and then we do. Okay, so next we'll see how to find vertex normal in the polygon data. Then we'll see much awaited. So surface normal we calculated, much awaited normal transformation. The relationship between surface transformation and normal transformation. Okay, so if I rotate this, okay, if I rotate this, translate this, rotate, translate or scale the surface, what about the normal? I mean, what I am trying to say, if I do the transformation on the surface, how much transformation we can receive on the normal? So both are not same. Transforming the surface and transforming the normal are not same. If I transform the surface, same transformation matrix I cannot apply on the normal. So what is the relationship? Okay, so that we'll see.
We have seen analytical surface. So this discussion is about surface and normal. So if I have a surface, then how we can calculate normal? So that is the idea. Later we'll see that if I have a surface and if I know the normal. So first is, if I have a surface, then how I can calculate normal. And then after the calculation, if a surface makes a transformation, then how much transformation we can expect in the normal. So two things. So while calculating the normal, we saw that surface is of two types. One type is analytical surface. We can say like analog surfaces, which is continuous, and discrete surfaces, also called polygon data, or which had facets. So calculating the normal of polygon data is also challenging. Means if I start calculating each facet's normal separately, and facets are little big, then there is a chance that there will be aliasing while drawing the shape. Means each facet has different normal. This facet adjacent to this facet, and this normal and this normal. So they will not look smooth. So even though I know that if I take a vertex on a facet, and then if I calculate the cross of two vectors, the vectors that are kind of they are associated with the vertex, then we get the normal. Okay, so the basic of getting normal is we have to find a surface, and then we take any two vector on the surface, and then we try to calculate the normal. So the story is same in calculating the normal for the polygon data also. We have different facets, and for each facet we take two vectors, and then we calculate the normal. Once normal is calculated, then if I take a kind of a point, like if I have a smooth surface can be like convex way, again convex, then there will be a sharp. Okay, so surfaces meeting like this. So here when they meet, the two surfaces goes like this. So we can say as a concave meeting, or it meets like this, that kind of convex meeting. So if it is a convex meeting, then we can take the average. Otherwise, in concave meeting, we have to go with the way it is. So anyway, that we'll see how it is. Now we have calculated the normal for continuous data, analytical surface and discrete surfaces. Now, then we'll move to story of if I have a surface and I transform it, how much transformation its normal can take. So why they are different? Yes. A normal has different transformation and surface has different transformation. Surface is not like a vector that we have seen. Means it's a surface. Okay, it can have if surface is a flat, then we can think about its direction. Okay, and if it is a 2D surface, then we can think about two directions. But a normal is normal, means it has one direction and it has magnitude. So I have a surface and I have a normal. Now I am rotating the surface, so normal is rotating. Okay, what is the relationship between these transformations? So if we don't understand this relationship of the transformation between the surface and normal, then when we go for light calculation, so whatever transformation we receive in the surface, if we apply same transformation in the normal,
then result would be wave, because that is not what actually it is happening. So these two cases we'll see. Anyway, we started with calculating the normal for a surface, and then so now we'll see for the discrete surface polygon data, and then we'll see how to calculate the normal if we know the transformation for a surface. That we'll see. Okay, so we'll continue now. So implicit. So we have seen kind of. Okay, so polygon data we'll see. Okay, so this is polygon data. We have seen implicit function, calculating the normal for the implicit function. Now we'll calculate. So this is polygon data. This is kind of triangular data, and where this is kind of a spherical, but okay, the facets. So these are quad, and now we want to calculate like. So there are many quads. Like, can we see this quad? I don't think there is a zoom. Okay, is it better? So now can we see this quad? This is yellow line and this is green line. So this quad, so we are talking about this vertices. Okay, so what's it? Now consider there are 4 lines of the quad. 1 line, 2 line, 3 line and 4 line. So in this quad, one is yellow and one is green. So yellow we consider vector as v1 and then v2. If I calculate, so this is flat. Okay, so this is not a kind of a round or spherical. So this is flat. All are flat. Okay, so all quads are flat. This triangle is flat. So if this is flat, then any two kind of vector, not vertice, any two vector I can take, and if I do the cross multiplication, then we'll get a magnitude and direction would be normal to. So this is the new norm. Okay, so that is the idea. Now this is point red. I think it's visible. So this is red point. Now this point, okay, this point we see nicely. Now we calculated normal of this quad. Okay, what about normal of this? What we are trying to do? Means I don't want kind of aliased. So if I do the calculation with all these normals, okay, if I do the calculation with all these normals separately and these areas, these facets are kind of big, then there will be alias. It will look like it's not a smooth sphere. So for that we take the vertices, like this is the vertices, and around these vertices there are 4 facets, 4 quads. Now we named it as N1, N2, N3 and N4. And we'll calculate N1, N2, N3, 4 and then we'll do average, or we will calculate N1, N2, N3, N4 and then we'll have weightage. Like if angular weightage also we can give if some normal has more angle or something like that. And then we divide by 4. So by weight or by normal addition and they divide by 4. So these two we can do to calculate the normal at. So this is okay. So this is normal of any facet. Okay, so this is normal of any facet. So I can say this as facet sum f Okay, so this is for f, not very small, and so what I mean is f is this. So this is kind of normal for the any particular facet, and now we are calculating normal of a vertex. So this is normal of a vertex. Normal of a particular vertex. Okay, or normal of a particular point. So okay, so this is normal of a particular point. So like that, for every point, what we see now here. So we can calculate like all four facets around it, neighbors, and we calculate their normals, and then we do the averaging. So this is the way we go for polygon data. Now consider this as a kind of a surface. So it's like a book. Okay, so left page and right page, and this is a curve. This is a curve, and this down we can see the kind of we can say like deep. Okay, so it's a deep line, and then it's a kind of high altitude, and these are the surfaces. Now in OpenGL for the polygon data, if it is a quad, then if I am calculating for the P, so this is a point P. If it is a point P, this is P, then all four normals, this is convex. So all four normals we have to calculate, and we have to do averaging. What about Q? Same thing we have to do. It is a kind of edge point on edge. Still we can do N3 and N4. But if it is in a kind of, okay, so it's a kind of deep ridge. Then if R is there, then we cannot do averaging around it, means it will be absurd. Then we have to show the neighbors separately. Okay, so that is the idea. Okay, so if we take care, then our kind of this polygon data would be kind of shown as a full sphere, okay, smooth sphere, where if we do the averaging, so first we calculated the normal, okay, any facet we took, and if I take a facet, then any two lines, they are kind of meeting each other, and then those two lines equation we calculated. How we calculate equation? It is the same as if two end of the line, okay, so two end of the line is P1 and P2, and if I subtract, then I get the vertex, I get the kind of the vector. So here also, if I subtract two end of the yellow line and two end of the green line, then I get V1 and V2. And if I get V1 and V2, then, okay, so we calculate the normal by crossing it. Okay, like that we get the normal of all the facet. Now rather than going with the facet, we go with the points, and each point's normal we calculate like averaging the neighbors' facets. By weight also we can do. Okay, so this is for the convex points or for the edges, but for concave, for the deep points, there this fundamental won't work, and we have to show the facets normal only. Okay, if we do, then we get smooth. Okay, so that is the idea. Okay, little bit, I believe I can show this. So I believe I can zoom it. Now okay, so this is, if this is okay, so if this is P1 and this is P2 and this is P3, we have not taken care of the kind of okay, so hand palm rule of the direction of the normal that we generally use. Okay, that should be considered. Now we have P1, P2 and P3. Okay, I think it's visible. Then if that is the case, we did it wrong place. Okay, we intended here. So same thing, I am not going to zoom now. So I can say this is P1 this is P1, this is P2, and this is P3. Okay, if that is the case, then we can consider V1 as kind of P1 minus P2. And here V2 means P2 minus P3, P2 minus P3. So this is the way kind of we calculate the vectors, and then we do cross. Everywhere cross is there. Here also we did cross. Okay, so we have to find the surface, and the cross of the surface is normal, and then smoothing we can do through averaging, and then we can reach like this. Okay, so finally earlier we were in kind of calculating the normal of a surface. Now surface transformation and normal transformation. If I have a surface like this, and if I transform the surface, what about the normal? How it would transform? Okay, so that is the question. So if I have a surface, so this is a surface and this is the normal. I am transforming the surface, normal is transforming. I am transforming the surface and normal is transforming. Okay, so now question is, if this transformation is X, means surface transformation, and this transformation is Y, then what is Y? Okay, so in that case, what is Y? If X is the transformation in the surface, then what is the transformation in the on the normal? So that is the question. Okay, so that we'll see the calculation. Okay, now I have a surface and V is any point on the surface. if I have a surface, okay, if I have a surface, then V is any point on the surface. So V is any point on the surface. Okay. Now, if n is normal, okay, so Mr. Surface is different here and there. So I'll make it V being here. Okay. Now I have a V that is a point on the surface and n is the normal. If that is the case, then n dot V would be 0 because normal dot product of two vectors is 0 if it is 90 degree. If they are orthogonal, then it is 0. Then if I turn it to matrix multiplication, then I have to transpose it, one of them. Then I can insert identity matrix, doesn't matter. If it is identity matrix, then it is nothing but, so there is a kind of a matrix M, then matrix inverse. I can be replaced by M inverse and M. So M inverse and M multiplication is identity matrix. Now I group it separately. Now if M and V is there, I can say that the vertex is moved by or transformed by matrix M. If that is the case, then this is, okay, so this is kind of a new surface. This became a surface. Means what I am trying to say is, okay, if there is an equation called S equal to 0, that is the equation of surface. If S equal to 0, okay, then any point on S, okay, so S into V equal to 0. So it should satisfy this equation. Okay, if that is the case, then if this is a new vertex position, means transformed vertex position, then it lies on the plane nt and m minus 1. Okay, but we are interested in normal. Okay, so if this is the plane, okay, now this is equivalent to m to the power minus 1 inverse transpose n and then total transpose. So this leads to our kind of this formula. Okay, if this is the vertex and this is the transpose and it follows the equation, then if this is the new vertex, if this is the transpose, then this is completely new normal. New normal in the sense that, okay, so if this is the new normal, okay, then this is the, okay, so this is the kind of the new transformation. Okay, so whatever is inside, okay, that is the new normal. That's why then this was the normal, then this got multiplied to this. So what we are trying to prove this now, V vertex transformed by M, then Mr. Normal got transformed by inverse of M and then transformed. So first we do inverse, then we do transpose, that much it transformed. So Y is what? If it is X, then Y is X inverse and transpose, so we'll fill it. Y is what? Okay, so Y is nothing but Mr. X okay, and then inverse and then transpose inverse and transpose okay. So then we can say that y would move like this. So y is new transformation matrix, then it is like this. Okay, so that is the scenario. Okay, we'll really rotate it, and this is how we'll see many more things. So slowly, okay, so okay, so this is the kind of idea. Now I have a Python program. Now this is the normal, and normal is in direction of y, and our surface is in kind of xz plane. So I am going to rotate it. So this is the surface. So the way surface is rotating, normal is also rotating. Okay, so if surface is transformed, this is one transformation. Okay, this is another transformation. Can we see? Okay. Okay, now we can scale it. That was GLU, that was perspective projection, so that's why it was looking like that. All are transformation, not one. This is, okay. This is one transformation. Now, this is another way of, both are, one is local and one is grand transformation. So many transformations. So this is the relationship. If I have a normal and I have a surface, and okay, this is one transformation. Can we see how it is going in the direction of normal? And this is another way of transformation. Okay, there can be many transformations. Okay, so I don't know if it is really, it happens. Can we see? This is another way of transformation. Okay. This is another way of transformation. Okay, this is local. Okay, so story is that how much it transforms when we transform the surface. If that is in question, then this is the solution. Now, kind of more towards C in kind of more examples. Okay, so if we transform the surface by M, then we have to transform the normal by inverse and transpose of the matrix. If we don't do, then they will get misaligned. So that is the idea. So that we have seen. Okay, so quickly I'll just recap what we have covered. So we started with kind of surface and normal and how we have to calculate the normal for the analytical surface. We calculated the normal by first calculating the tangents, and then we get a plane and then cross, we get the normal. And it is also in explicit and implicit way. So this is explicit way where we don't need z coordinate, or implicit way where we have to find the gradients and then we do it. Okay, surfaces are two types. For polygon data, for each facet, so we have to calculate vectors and then we calculate the kind of normal by crossing it. And then for each point, neighbors, facets, normal, we average and we get it. Points can be convex, concave or edge. And then for the convex, we take the care of the neighbors, for the edge also, but for concave or for the deep points. Okay, so we have to rely upon the neighbor. Okay, so it become really smooth. And then we calculated the normal transformation if there is a transformation in the surface, and that leads to, if there is a transformation of M in the surface, then there is a transformation of, okay, so inverse of the M and then transpose. Okay, what we'll see in the future session. So in future session we'll see like matrices, like what is actually M and what is actually V and what is actually N and what is M. So these matrices we will kind of we will open the matrices. Okay, so we can say like unbinding. So we will unbind the matrices and we'll see that how it happens, what is inverse and what is transpose, and then how actually it works. So that will see. We have seen now the analogy of calculating the normal of a surface and then transformation of a surface that comes to transpose and inverse of the transformation matrix, that if a surface is transformed by a matrix, if I calculate inverse and transpose of that matrix, then that comes to kind of the transformation for its norm. So if I am calculating, like I calculate light vector and I calculate spot direction, then I calculate I vector, which from I to, there are so many vectors we calculate. Okay, but when we think about the surfaces, then we go with the normal transformation. When we see about like a spot angle is one of them, which is kind of, or a simple normal when we calculate, like when we go with the diffuse calculation, then light and simple normal, that L dot M. So simple normal, or if a surface is transforming, then how normal transform
Or if light is source is transforming, then how it's a spot angle will transform. So both cannot be same, and it is transpose and inverse of the surface transformation matrix. What is surface transformation matrix? Okay. What is the story behind the curtain? So OpenGL is nothing but it's a game of matrices. Okay, so OpenGL stuff, they invented few matrices. Like if someone transforms, then it will transform. If someone transforms by 20 in x direction, okay, I have to transform in x direction 20. So this is the input. And another is transformation matrix for the transformation passes through the media, and the new output is the transformed one. So what is this matrix? Transformation matrix for what is matrix for the transformation? What is it? What is it? Or if I do scaling, if I do rotation, if I go for orthographic projection, if I go for perspective projection, what matrix, the media in the, you can please refer matrix tutorial. So where input get kind of transformed, input get mixed with the kind of media and it changes. Then what is the media? So media is different from translation, rotation, scaling, perspective, orthographic projection and everything. So OpenGL is a game of vertices and OpenGL is a game of vertex transformation. So if I do transformation in translation, if I do transformation in rotation, and if I do transformation in the scaling, what happens? Okay, so if I see the inside the story of the transformation, if the input goes and it do correlation with the or matrix multiplication with the transformation, separate media or separate transformation matrices, what happens? If we see little closely, then you will really understand the difference between surface and normal. What is a surface and what is a normal? If we understand the basic difference between surface and normal, then we can avoid transpose and inverse. Probably this is not possible anywhere. This discussion has never happened anywhere. So that we'll see that if we have transformation matrices, and then if I do transformation of a surface, means vertex on a surface, what it does, and if I do transformation on a normal, what it does, why it creates problem when we go for transformation with normal matrix and we need transpose and inverse. If that problem, if we sort out, then we can reduce lots and lots of calculations. Means just think about a calculation. If we don't put this calculation transpose inverse, and then we have to put in shader, then we have to put in the code partition. Still, every movement of one, if I don't go for multiple color bubbles, single color bubble, and then for each movement of each item, it draws all the items. One item is set of VA. If my scene if my scene has 2000 items, just think that if one item moves 2000 draws, 2000 times transpose and inverse gets calculated.
Okay, if I am not going VAO wise also, per item, every point. Now, if in 1 second, if it moves 10 times one, one item, how many matrix multiplication we need to do in the CPU? If I place in GPU, we can place in GPU, okay, but it will happen per vertex and per fragment. That is another problem, okay, because GPU, that shaders get caught per vertex in the, not per VAO, per vertex. So per vertex vertex shader and per fragment shader. So we can't afford doing this kind of transpose inverse there. So we have to do in CPU only. And if we do CPU, each draw 1000 times we have to calculate transpose inverse. Think about the expenditure. Okay. So if we go little in depth, can we save it? If we understand the different medium, please refer to the matrix tutorial. We talk about the different vertices and then different kind of media and output and input and so many. Then we can really save lot of CPU time and it will be faster. Graphics is kind of, it makes sense when it happens, anything, if it happens in time. Otherwise, if I draw something and it takes more time than we expect or we have given to it, then what will happen? Nothing will happen. It will start dropping the frames. You will lose the information. So why to lose information when it is not required? So that we'll see. Okay, so we'll proceed on the surface normal and normal transformation. So we have we have seen that the surface and normal are two different things, and any vertex on surface is it's a vertex, whereas normal is a direction, so normal is a vector. Okay, so there is a vertex. This is a point on the surface, and this is a point, whereas normal is a direction. This is a point, it has coordinate, but normal has no coordinate, it's a direction. Okay, so if there is a transformation on the vertex M, then normal transformation, the normal happens as inverse of the M and then it's transposed. So this is what we have seen. So this is the story right now. Okay, so now we'll move. Now if this is the surface, then this is the normal. So surface, like generally it has we can say that, okay, so V is a point on the surface, but surface has area and minimum the set of vertices that form an area. So that is a triangle. Okay, so this is surface and this is normal. Okay, what we can do on the surface? So we can translate the surface. So surface is here and surface translated to here. So surface can be translated. Surface can be scaled. Now it has become smaller. Surface can be rotated. So surface can be translated. It can be rotated and it can be scaled. So three things on the surface is possible. I believe I can show it. there is nothing. Okay, so we can see surface and normal on the surface. So if surface is kind of now surface we are translating. Okay. So these are translations. Okay. Now I can scale the surface. Scale down. This is translation. Scaling. Scale down. Or I can rotate the surface. Okay, so this is the concept. Now, in kind of matrix tutorial, we have seen that if there is an input X and there is a media or matrix in between and it constitutes Y as output, then we can say X multiplied by the matrix is Y, means X is passing through the media, and this input, if I multiply with M, then it becomes Y. Okay, so nice it is. So this is about this. Now what is X? So input is in form of X, Y, Z and W. This is the fourth parameter, and typically we divide everything by W. Now if input is like this and W is 1, then there is a point. If W is 0, then certainly this point is on infinity, because divided by. So this is the kind of concept of X. And then M, media, is a matrix. So if X passes through media, it becomes Y. What is the media? Okay, so if we are translating, then it has to pass through this matrix. If we are rotating, like for example, so translating X, Y, Z is kind of fourth column. And if I rotating, so I have taken example of rotation around X axis, then it has to pass through this matrix. If I am scaling, then it has to pass through this matrix. If I am doing GL frustum, means perspective projection, then it has to pass through this matrix. Okay, can we see that it changes? Like if I just translate on the right side, can we see it a little bit? It is rotating. See? Even though I am just translating, so this is perspective projection. So the input, okay, the input is passing through the matrix. Okay, so when input passes through a matrix, it changes. So if it is translation, it has to pass through this matrix. If it is rotation along x-axis, it has to pass through this matrix, scaling or perspective. So if I have an input X, so X is like in kind of electronics, or so these areas, X is typically the input, the current level or voltage level, and media is a set of resistance through which it passes, or in communications, like it may pass through some media like air or any media. Okay, so signal gets distorted, but here in OpenGL, X is nothing but a coordinate and media is nothing but matrix. So a coordinate, if passes through a matrix, it changes. What is the matrix depends upon what we want. Okay, so from translation to rotation to scale and then perspective projection. So that is the story. Okay, let's try. Means kind of I am translating. So if I am translating X, Y and Z, all three, and I have input as 0, 0, 0. So the point is kind of it is at origin. If it is at origin and I am translating X, Y, Z in three directions, then new point is X, Y, Z. Can we see? Means I mean it's simple multiplication. Okay, if two matrices are multiplied, it is X, Y, Z. So new point. So new point. So what I want to say is okay. So if there is a coordinate like this, okay. So probably red is x-axis and green is y-axis and z is blue. Okay, and I have a point at the origin. Okay, if I translate it, okay, in x direction, y direction, z direction, this point now it would sit somewhere here as per the translation. How much it would shift? If there is a translation of x in x direction, y in y direction, z, so that is the new coordinate. We change the coordinate from origin to new origin. How it changed? It just multiplied by a matrix. That's it. Okay, now what about if there are two media? Input signal passes through a matrix and it becomes output signal. Output signal passes through a matrix and it becomes a new output. So this output becomes input to the second media and this is the story. Two matrices. Input first multiplied by matrix 1, that become input to matrix 2 and that is the output. But in OpenGL, first we specify matrices and then we provide the actual drawing like what is the vertices. So it is opposite way. If we specify in opposite way, it happens opposite way. So first input is multiplied by nearest matrix and then multiplied by M2. Okay, I mean I can see this. So whatever the program we wrote now here, so I'll do kind of some okay, so in display we are translating minus 15. So I think we have already so before translation what is the model view matrix and after the translation what is the model view matrix. So we'll see that. Okay, so before translation it is unity, unit matrix, 1, 1 in the diagonal. Okay, and after the translation can we see minus 15, that is in the third row, this is the first row. Okay, so probably I can print it in different way. Before translation and after translation. Okay, so before translation, and after translation. Okay, so far better. Now it is kind of a unity matrix. So whereas after the translation, can we see x, y and z. So z components minus 15 happened because I did translation of minus. Okay, so this is the story. Now I'll see the code. So when it enters, first thing we do is minus 15, like in this reshape. Whenever it reshaping, we are loading the model view, setting it identity. So it's identity matrix. And in the identity matrix, now we kind of we translating by minus 15. If I am translating by minus 15, everything is going in minus 15, means from the origin it is shifting minus 15 in the minus z direction. Okay, so if I do kind of minus 55, okay, so it will start very small at the beginning only. Can we see? Okay, so see the size. So it went far. Okay, so it went far. Okay, so I can translate it in minus z this much and x 20. So it automatically it will go right. Not okay. We can see it is at right. Small and light, right? Now we'll make it kind of left and big. So I will say left, and it should be bigger. So only minus 5. Okay, I believe it is very big and it did not appear. So not that that big. Okay, so I'll make it kind of, or minus 20 it became too much. Okay, for big. So I'll say minus 2 and try. It should be on left side. Okay, so far better. So it is on left side and it is very big. So this is how it's happening, because it is passing through translation matrix. Okay, so now the item is at 0 origin and we are passing through the translation matrix. Okay, now story is if there are two matrices M1, M2. In OpenGL we specify M1, M1. So we specify matrices first and then drawing happens. So this is the input right side. It multiplies with matrix 1 and then multiplies with matrix 2. Okay, so what we can do is we can kind of rotate and then translate. Okay, so okay, so this is how it is. So GL translate. Okay, so we rotate 30 degree along y axis. Okay, and then we translate minus 2. Let's see. I think GL translate will give it kind of minus 15, so it should be nicely visible. Okay, so it should be kind of translated. Can we see? At the beginning only it is translated. It is rotated. So first it is translated, first it is rotated, and it is. So this is happening in kind of a grand coordinate. So please refer transformation tutorial. Okay. So there we talk about local and global or grand. So this is transformed through the global. Okay, so that is the story. So if I have a kind of, we can see what it printed. Okay, so before translation it was identity matrix. After translation, okay, this is minus 2x minus 15, that is z, and these are angular. Okay, rotation it made. So this is how it made. So we can see translation and rotation both inside the matrix. Okay, so if there is a drawing and there is the input, there is a media, first it kind of do the matrix multiplication and then do matrix multiplication. If we through local coordinate system, then there is another way from looking from left to right. But actual matrix multiplication happens from right to left because the input is on the right, output is on the left. So it starts from the right and proceed toward the left. Okay, so if I am rotating along y-axis, so let's rotate along x-axis the way we have. So we'll rotate along x-axis 30 degree and we'll see the matrix. Now matrix we can see like anyway minus 2 and minus 15 is x and z, and this is cos 30 minus sin 30, sin 30, cos 30. Okay, this is what it is. Cos 30 minus sin 30, cos 30, sin 30. Okay, so this is what we are seeing, these two. And this is x translation, y translation. So, okay, so it's a play of matrix, nothing more than that. So now we are kind of multiplying by rotation and translation. Okay, so as per the formula, x is multiplied by matrix 1 and then matrix 2. So if x is 0, 0, 0 and 1, it is multiplied by a matrix, rotation matrix, whatever comes, then it is multiplied by GL trans. So this is the story. Okay, so what we can see now is if I have a coordinate 0, 0, 1. So there is one example, like if I have a coordinate 0, 0, 1 and 1.0, so z is 1, x, y is 0, and if I transform, okay, translate x, y, z, then it will be x, y and 1 plus z. So z is kind of changing. If I am in the input, the vertex is 0, 0, 1, z is 1, others are 0. Transformation, the translation happens only in z. This is what we are seeing. Okay, now kind of let's see the rotation. Now same 0, 0, 1. So point is 0, 0, 1. Okay. If that is the case, then if I rotate along x-axis 30 degree, then it becomes 0. Okay. So this is the along x-axis A angle. So that will become 0 minus sin A cos A 1.0. It's a simple matrix multiplication. If I translate a point 0, 0, 1, it will become like this. If I rotate 0, 0, 1, it will become like this. Okay, so I think we can just keep our breath. Okay, now we talked about two media and two media in OpenGL. Now, can we remember if there is a transformation of M in a vertex position, then there is a transformation of M minus 1 inverse and then transpose in the normal. So if I do transformation of M in the surface, then normal get transformed by inverse and transpose of the transformation that happens in the surface. Okay, now we see the transformation of the vertex. We gave example that if vertex is like this, like 1, then how it will transform if it is translation, and how it will transform it is rotation, if it is rotation. Okay, so if input is 0, 0, 1, what will be the output if it is rotated? If input is 0, 0, 1, what will be the output if it is translated? Okay, now this is the vertex transformation we saw, and net transformation follows this rule. Okay, input is multiplied by the last. So if I take our code example, then input will be multiplied, first this matrix, rotation matrix would be multiplied, then translation. We are doing translation first, then rotation, then we are drawing it. Okay, so this is rotation matrix and this is translation matrix. So, okay, so we saw that this is how it happens. First rotation get multiplied and then translation. Anyways, now let's move kind of how the normal would get transformation. Okay, now I have input of 0, 0, 1. Okay, how normal would get transformation. So this is in normal. Okay, so this is the vertex point, and now if I want like, okay, so if this is the kind of a point on the surface 0, 0, 1, and this is the matrix we are doing the transformation, means what I want to say is, if I am doing transformation of M in V, then there is a transformation of inverse and transpose in the normal. Okay, if that is true, then this is M and this is V. Now we have to find transpose and inverse of this. Okay, so inverse of this is this, and if we do the transpose, then this will come here. Okay, so transpose of the translation is like this. Okay, now if I do the calculation, okay, can we see it is unchanged? 0, 0, 1. 1 is the fourth coordinate. There is change only in the fourth coordinate. Can we see? If I am doing transformation, plane transformation, then there is a change in z coordinate, 1 plus z, and x and y also got introduced. So 0, 0, 1 got translated by x, y and z. Can we see this very clearly? New point is it has x field, y field, z modified. Z also got added. But if I do transpose and inverse of the matrix, and same thing, so first we calculated the inverse, then transpose. Okay, and now transpose inverse, if I multiply with the same point, there is no change. Can we see? There is no change at all. It remains unaffected. Only the fourth parameter, so that we can divide. I mean, if I normalize it, is pretty well, it is same. Okay, let's do transpose and inverse for the rotation. So, okay, we have not done transpose and inverse of the rotation. Okay, anyway, just leave it. Okay, now we have done transpose and inverse of the translation, and we see that nothing changes. Now, I have a matrix, I have a kind of two media. One is translation, one is rotation. Now, all together we will calculate inverse, transpose. After calculating this, then we will multiply this with the input and we will see the output. Okay. Okay, so this is not what we want. So there is no output here, output should not be considered. Okay, so probably I can modify this slide. Okay, so what we are trying to find is, I think we can just leave right side for right now, or we can just modify. There's no harm. Okay. Okay, so we are calculating this, and that will find the output. Okay, now I have two matrices. One is rotation and one is translation, and we have already calculated this. If it is only translation, if it is only rotation, okay, or we have also calculated if it is kind of rotation and translation. Okay, now we will do the we'll calculate the net matrix in the for the normal, so that will be inverse and transpose whatever we get. So this is okay, so this will calculate the okay. Now I think font is pretty small, so we'll do these multiplication. Okay, so this and this, whatever we receive, okay, then we'll do inverse, and then we will do kind of transpose. Okay, so I should have removed this line also. So we'll just calculate the transpose and inverse of the matrix. Okay, so then we will probably we will multiply with the input. Okay, so what we are trying to do is M1 and M2. Okay, so this we will multiply and we will calculate the transpose and inverse, and we'll see that what is the effective matrix. Okay, so what we are trying to do, so this we can also write, probably we can, okay, so okay, so okay, what we are trying to, so we can just have it, and what we are trying to find is okay, okay. So now I have two matrices, M1 and M2. Okay. So M1 and M2, they constitute a matrix. We are trying to get the transpose and inverse of M1 and M2. So if input is transformed by M1 into M2, then how much the normal would get transformed? That is nothing but transpose and inverse of these two multiplication. Okay, so by now we have seen this much detail where we did the transpose and inverse of a translation, and now we are doing the transpose and inverse of two matrices, translation and rotation, and we'll see the effect on the input of the transpose and inverse. Now we'll multiply with these two. If I multiply, it becomes matrix like this. So now I have to find inverse and transpose. Okay, so what is the inverse of a matrix? That is adjugate of a matrix divided by its kind of magnitude. Okay, that is the inverse. So this is kind of called cofactor. So cofactor of the matrix we have written this big. If this is the matrix, this matrix we have received after multiplying translation and rotation. If there is a translation and rotation on the surface, how much translation and rotation would happen in the normal? Okay, that is the calculation. For that, we are calculating transpose and inverse. So first we multiply these two, and if we multiply these two, it comes to this stage, and if I want to inverse it, then I have to calculate the cofactor of each entity, this big. Okay, so if I get the cofactor of this entity, okay, then I have to do the transpose. Now I have taken x equal to 0 and y equal to 0, z equal to 1. This is what we want. Okay, so we are calculating for x0, y0 and z. So this one we saw that if I do the normal translation, then this is the kind of new vertex. If input is 0, 0, 1, the new is x, y, 1 plus z. if I do kind of transpose and inverse, and if I do multiplication, then modification only happens in the W, whereas in the surface, okay, modification happens everywhere, but in the normal, modification happens only in the W. What about this? Okay, so it leads to this matrix, and now we have to calculate T, but we want only for x0, y0 and z equal to 0. So if I here, now I'll if I move ahead and then I calculate it. So what we are doing here, if this is the kind of cofactors, so this is one matrix, this is one matrix, these are cofactor of the bigger matrices. Now I have to calculate the determinant. So if I want determinant, then I have to keep this and multiply these diagonals. Then I have to keep this, multiply then whatever the determinant comes. So like that for every matrix we have to do, and we did. For every matrix we did, keeping x equal to 0, y equal to 0 and z equal to 1. So it comes to cos square a plus sin square a, and then like this, and then cos square a and sin square a. So this much we got. Now we have to calculate transpose, then again transpose. So inverse is, I have to find cofactors, and once we calculate the cofactor, I have to do the transpose. Okay, so net if I see the transpose and inverse of the matrix, then whatever we have received after calculating the cofactor, that is the adjugate matrix, I am not calculating the magnitude. Okay, so if this is the magnitude A by magnitude, so I am not calculating the magnitude. So two transpose. One transpose anyway comes in the inverse, again transpose. So they cancel each other, and we get this as kind of transpose and inverse of this matrix. If I have a translation matrix and rotation matrix, and I want to calculate the transformation in the normal, then I have to calculate transpose and inverse. So if I calculate the transpose and inverse of this matrix, it results in this. So cos square a plus sin square a is 1. Cos square a plus sin square a is 1. And then others. So this is the net matrix I am getting after transpose and inverse. Okay. So if I see here, for the simple translation, if I do transpose and inverse, I get this as net matrix. If this is the matrix, then this is the net matrix. Then first with the original matrix, I multiply the vertex, I get new vertex. But after doing the transpose and inverse, if I multiply the vertex, okay, then I get, if I multiply the normal, this is normal. Normal is unchanged, only W changes in the translation. But if translation and rotation both are there, then this is the new matrix. Okay. Against these two, if translation and rotation are two matrices, their transpose and inverse comes to this matrix. This is a matrix. Okay. Can we see a kind of have we seen this matrix around? Nowhere. Okay, so we have not seen this matrix anywhere. So very fine. Let's go for multiplication. So if this is the matrix, okay, and I multiply this with the if I have a normal like 0, 0, 1 and z, this is what we are seeing. This is what we are doing. Okay, so I have a 0.001, 1.0. So now we will do the computation. Okay, so now time has come that if this is the matrix, if this is the matrix, if this is the new transpose and inverse matrix, now we have to kind of do and the new points are the input points are 0, 0, 1 and 1. Okay, 1.0. Okay, now if I multiply, okay, so this with that, so this can be represented like this. This is input. Okay, now can we see that it would become, so we'll do the computation. Okay, so first row of the matrix and first column, if we multiply, then it will become 0. Next, if I multiply, then it will become minus sin A. Next, if we multiply, then it will become cos A. Okay, if I am right. Next, if I multiply, then it would become minus cos A plus 1. Okay, so this is what we are getting, 0 and minus sin A. Okay, then minus cos A. Okay, cos A, then minus cos A plus 1. So this is what we are getting after doing the okay. Now if I take x, y, z, 0 minus sin A cos A, okay, w we leave it. Now can we remember something? If there is a rotation, okay, then minus sin A cos A, this is the way it modifies. Minus sin A cos A, minus sin A cos A, and if we see the matrix, it is exactly same if I leave the fourth row. Okay, so fourth row, if I exclude, then top 3 rows are same, and that's why we are getting same thing. Can we see? Okay, so in the matrix, top 3 rows are same. Fourth row is different. This is the translation row. Now, if I have two matrices, translate matrix and rotation matrix, and if I do transpose and inverse of these two matrix multiplication, it comes to a matrix where there is only rotation. That what we do, the translation, it comes as fourth row, which has no weightage. It just compute in the W. Otherwise, it is only angular. Can we see this? This proves that transpose and inverse, it is affected only by rotation, not by the translation. That's why we do transpose and inverse. Okay, if there is a vertex and there is a transformation M, then in the normal there is a transformation inverse and transpose. What is inverse and transpose? Inverse and transpose is nothing but only rotation. There is no translation. Can we see this? If I translate, normal doesn't change. Normal is a direction. If I scale, normal doesn't change. But if I rotate, normal changes. That's the difference between the kind of surface transformation and normal transformation. Surface transformation changes with translation, it changes with scaling, okay? It changes with rotation, but normal doesn't change with the translation and scaling. It changes only if I rotate, okay? Now, I can't afford transforming normal. If I am transforming a vertex by M matrix, I cannot afford transforming normal also by M matrix. If I do so, can we see in the calculation? Okay, so in the calculation, if I have a vertex 0, 0, 1 and there is a transformation matrix, then can we see if I do simple multiplication, it fills XYZ. Means normal direction is changing if I do the translation that I don't want. Normal direction must change. Okay. So if I comment this, and I execute this code, okay, normal is changing. If I do translation, normal is not changing. Can we see? It is same. If I scale it, it is not changing. Normal direction is same. But if I rotate, normal is changing. That's the difference between point on the surface and point on the normal. Normal must be modified only when there is a rotation on the surface. Otherwise, it should not be modified at all. Okay, so that is the scenario. Now, what I am trying to prove now is, okay, very nice. Now I have calculation wherever I want to do the rotation on the normal, I have to calculate transpose and inverse. Blindly we cannot do anything, but not required. Transpose and inverse only brings the rotation part. Okay, so can we say like this? If there is a model view matrix, if there is a matrix M, inverse and then transpose. If I take out the matrix part, okay, so it's matrix part, matrix 3 means top 3 row and top 3 column, and its rotation part top 3 row and top 3 column, they are same. Okay, and now if I see the matrices, the beginning translation changes fourth column. If I do transpose, inverse and transpose, this fourth column becomes here in the fourth row. First 3 row and first 3 column, they are only for rotation and they never change. Okay, anywhere, see. So first row, 3 row and 3 column are unaffected by translation. They are modified only kind of if we do the rotation. Okay, if that is true, Okay, if that is true, then whatever the transformation we do on M, same transformation we can do on normal. If I take out only the first 3 row and column. Okay, so if like in the OpenGL shaders code, okay, like I'll show my kind of shader software code. Okay, generally what we do, we calculate transpose inverse of the model, and whenever we have to do transformation in the normal, we go with the transpose and inverse. Transpose and inverse are calculated as transpose and inverse of the model view matrix that is passed to the transpose inverse view. This much calculation we don't need. Okay, if I have plain model view space, plain model view, like there are 3 things: coordinate, normal and texture coordinate. So coordinate get transformed by model view matrix, whereas normal get transformed by transpose inverse of the model view. We don't need. We can save lot and lot of CPU computation. What do? We just take out the matrix top 3 row and column of the model view sphere to calculate the transformation in the normal. Okay, so normal, the transformation what we receive in the normal is nothing but only rotation. That is the kind of top 3 row and top 3 column of the model view matrix. We don't need. Okay, so we don't need any calculation of transpose inverse at all. In lighting also we don't need. In lighting also we are just passing the simple model view. Okay, can we see? Means if I am doing the spot direction, only first 3 we are passing. Okay, so like a spot direction is a direction. Spot direction is like a normal, it has direction. Only first 3 we are passing. If I see the fragment shader, we are not doing any calculation at all. Okay, there is no kind of there is nothing as model view lighting and transpose inverse of lighting, nothing. There is no transpose inverse at all in the shader code, not required. This saves a lot. This kind of do the high speed kind of graphics. Okay, probably this cannot be found in any book. Means anyone can understand. Means this is local. This is not international. Okay, so this can be kind of we can achieve, like if I am doing any transpose and inverse, we land up in the same top 3 row and column what we see in the rotation. Okay, if we are doing a rotation transformation in the M, if vertex is transformed by M, we can take out top 3 row and column, and that's it, not required to calculate transpose and inverse. That is the normal transformation. This computation is not required. Means this research what has been done by people this much, whatever we saw in the training, all are useless, not required. See how much we did calculating the transpose, and this much research we did from the first slide, how to calculate normal, and then this and that, and then we moved ahead, and then finally we came to conclusion that if a vertex is transformed by M matrix, then normal must be transformed by transpose inverse and transpose, not required. If a vertex is transformed by a matrix M, then we can just take the top 3, okay, and that is the transformation on the normal. This much mathematics is not, is not required. This is what we find in all internet and all the 3D books. Okay, so people they just mug up. Okay, so this much model view, and the shader code what we see, it is completely kind of untd with transpose and inverse here and there, calculating, and in the lighting calculation transpose and inverse in the then we have to specify from the Python code transpose. Means people that do, they die in this kind of nonsense. Not required this much. Many research are not required. Okay, so conclusion is whatever we have done, this much to show not required. Okay, so if I do transpose and inverse and transpose to find the kind of transformation in the normal, not required. Whatever transformation we are doing on the vertex, just we have to take out the top three. That's it. This is what we are doing in our vertex shader. Can we see this? Mat 3. Whatever model view transformation we are receiving for the vertex, like vertex is transformed by model view, same we are doing, just we take out the top three. And for the kind of spot direction, okay, in the Python code, spot direction in the Python code, whatever we do, we transpose anyway we do, because OpenGL stores in different way. We just take out the first three columns. Okay. Earlier we were also doing a transpose and see, transpose and then inverse. Okay, and in the kind of model view sphere also. Transpose and inverse, not required. Okay, so okay, so that is the concept. Anyway, with the new whatever the new algorithm is, means a kind of I can move ahead to publish this. So with the new algorithm, we have done all the solar system videos. So whatever we are kind of published in the solar system, moon rotation and whatever we have done, all are through kind of new calculation, not the traditional one. Okay, so I have another one. Okay, so this is lighting model, and where we are not calculating transforming normal by transpose and inverse, the way it is mentioned everywhere. Okay, in books also you will find why transpose and inverse to the normal is required. We have not done any transpose and inverse. Okay. Okay, I believe it should be visible. Now there is a road and kind of two cars are there and tree is there. Okay, so first car, if I turn it, can we see the lighting effect? It is perfect. And second car, if I rotate, then lighting on the tree are minimized. There is one default light that we have placed so that road can be seen. Okay, now if it rotates, it's a spotlight. Now it is illuminating the road also. Okay, same way, more light on the trees. Perfect. Car is moving on the highway. Okay, they are getting each other front light. Can we see their face is completely lightened? I mean, I can show like this. We can rotate complete thing and we can see each other's face. Okay, so probably Okay, so probably I can scale it down. Okay, now I can show each other face. They are lightened. Can we see? This face is lightened, and anyway other face is lightened that we saw. Now, first car is moving, and can we see? The headlight of the second car is not on the first car. Okay, I can make it bigger. Okay. Now first car is moving silently. If it happens to rotate, can we see the light it is throwing? All calculations are happening without transpose and inverse. Okay, I can rotate the first one also. Perfect. Okay, we can see the lighting on the trees. They are not perfect. It is better in one tree. It is better in both trees. Okay, so but it is required that we take out the top. It is kind of as a lab exercise that if I don't take out if I don't do the transpose inverse, then what we get? Okay, so if I don't do the transpose and inverse, okay, so if I don't take out the top 3 rows and if I don't do the transpose inverse also, then in the normal, if I do the simple matrix multiplication, it will fill up x, y, z. Okay, and it would not show the kind of, it will go away immediately. I mean, there won't be any lighting at all. Okay, so replacement of transpose and inverse, okay, so is kind of matrix 3. If I take out the matrix 3, top 3 and column, it is done. Okay, so this slide is like generally we find in the book also, if input is x, y, z, w, then these model view projection, the perspective and viewport transformation. So these are nothing but kind of media, and we have to multiply all this, and then we can kind of multiply with the x, y, z the way we did with the multiple media. So in the kind of transformation pipelining, so it also follows the set of vertices, and once it is multiplied with the input, then it results in kind of the output. Okay, so since beginning we saw how to find the normal. So a surface is there and there is a norm, normal is a vector has a direction, and we saw the kind of two things. One is analytical surface, one is polygon data. Any analytical surface we can find normal, one for the explicit surface definition, implicit surface definition. In the explicit we get the kind of tangents and then we make it cross and we get the normal. Okay, and in the implicit we get the formula in x, y, z, and then we calculate the gradient. Okay, and that we saw in the implicit. Okay, in the polygon data we saw that if we have points, we have a surface, then normal along the full surface. Polygon data is nothing but it's a kind of set of facets. Each facet has same normal, and we have to find two lines, and then we get the cross to get the normal. Okay, and now we saw that how we can kind of make it smoother, like for each vertices we calculate the average or weighted average to get, like, instead of this we get a smooth. Then we went ahead to calculate if we transform a point on the surface, then how much normal would be transformed. But later we see that this transformation is not required if it is translation and scaling, but it is only required if it is rotation only. Okay, if that is the case, then transpose and inverse we calculated. Transpose and inverse to calculate the normal, and we found that first three row and column is nothing but the rotation only. See, cos A minus sin A cos A. We started with cos A minus sin A, cos A, sin A. It end up in the same thing. Cos A sin minus sin A, cos A sin. Only fourth row is different. It makes different if this row becomes column. The way we saw here, if there is a column of x, y, z, then it fills up. But if this column is transformed into row, fourth row, it doesn't affect it. That's why we do transpose and inverse. Okay, so that is not required. If I take top three, okay, and then we do the math. Okay, so that's it.